Hey everyone, good morning, good evening, good afternoon, wherever you are. Please be welcome to a new experience of virtual tour at the Silla Observatory. My name is Pamela Marchand, and together with the producer Macarena Ordenes, we are going to be your guide on this virtual experience of La Silla Observatory at ESO. I'm a guide in the observatory since 2017, and I'm currently doing my master degree in astronomy. Um, any question you have, you can ask me. My field of research are galaxies. Uh, that's my expertise, but I love all of the astronomy. So let's say hi to Macarena and to get to know her.
Hello everyone, my name is Macarena Ordenes. I'm a guide in La Silla Observatory with Pamela, but I am a guide since 2019. Um, I'm an astronomy student with Pamela, but I'm not yet in a master degree. So any questions about astronomy, leave it in the comments. Also, any questions about the observatories, ESO, and all of that. Tell us where are you from. Uh, we have here some greetings from Scotland. Hello from Southern California. Someone who loved the intro. Yes, it's so beautiful. And here from Ireland. Nice countries. So, well, we have an hour here and we're gonna try to answer all the questions you have. And I think it's time to start.
Yeah, I think. First, we will travel to Coquimbo region in the northern Chile and visiting Isola Silla
Pamela, first
Observatory.
we have to know about the member states of ESO.
Yeah, that's my preview part to the to that image. I know that. So um, let's the tour begin. And we'll start with ESO member states, the European Southern Observatory, also known as ESO, which is an intergovernmental organization comprising 16 member states. And all of them are European countries. And recently, we have Australia that has become a strategic member. And with all of that countries, we have Chile, and Chile is the host country. It's not part of the ESO itself, but it's the host country. And this means that all of the observatories will be built in Chilean territory. So, since the 60s, with the purpose I mentioned, ESO chose one of the best places on the planet to carry out astronomy. And it's the Atacama Desert, where we have all of these places to do astronomy. And we'll start with Paranal. Paranal is in the near Antofagasta, and we have the currently most technology telescope right now, and we have the future ELT that will be built in Amazonas near Paranal. Then we have ALMA in the Chaclantor place. And ALMA is a radio telescope. It's not only for ESO; it's a bigger organization. And then we have ALMA and EPEX. And then, but not less important, we have La Silla Observatory, the one we are visiting today at Coquimbo. Eh, La Silla was the first observatory built in ESO here in Chile, and it was inaugurated in 1963. I mean, I'm sorry, in 1963, ESO chose Chile like the host country, as the host country, and La Silla was inaugurated in 1969 and is built at 2,400 meters above the sea level. So we're going to travel to the Silla Observatory looking at our planet. And we start our journey in Europe, since I must mention that ESO is a European organization founded in 1962. And this map outlined in white, we can see the different ESO member states. As we move as the Atlantic Ocean, Let me tell you a little more about of ESO mission. And to give you an idea, ESO tries to devise which type of instruments are needed to study the universe, and then design the pieces, build and operate all of the telescopes, responding to observational requests from around the world that encourage cooperating in astronomy. So you can see right now the place that belong to South America, and we are going to get to the southern, I mean the Andes mountain. This is the Andes mountain range, all of that brown part, and we are at the Atacama Desert, surrounded by Andes mountains at 600 kilometers north to Santiago, the Chilean capital, and 150 kilometers of La Serena. So, can you see those domes across the mountain? And look at the shape of the mountain that you can see better in another view. And I don't know if it reminds you of something. And this is the name of the of La Silla Observatory because the shape of the mountain reminds us to a horse saddle. It's called La Silla in Spanish. So we have La Silla Observatory over here, and we can see a flight over the observatory looking tiny telescopes, not tiny, but a meter of diameter telescopes, and like we have like 10 telescopes working at La Silla Observatory, but not all of them are part of ESO. Yes, for some universities and other organizations and operated by them. But the main the main targets of this tour are the ESO 3.6 telescope, the one in the top of the mountain. We have the entity, the one the video is showing us, and you also can see the CEST telescope in the right part of the video, and this is like the grandfather of ALBA. It's a radio telescope that it's no longer in use. So our flight is coming to an end, and now we are at La Silla Observatory. Start with this platform. Let me go into there. So we are now at 2,400 meters above the sea level, and this is the CEST telescope, 15 meters of diameter radio telescope, and in this plateau, so big, and you can see the entire observatory, all of the little domes. So let's go inside the 3.6 telescope, and it's commonly called that by the staff because of the the diameter of the primary mirror. But first, we are inside the telescope, and you can see that it's really huge. For example, we have the dome in this part, the ground, and I don't know if you can see anyone in this picture. So let me help you zooming in the image, and you can see here a person. This is an operator, and this is they are the one that operates the telescope. They are called, and they need to move the telescope, fix it if there is any problem, and they work together with astronomers during the night of observation. So it's really huge. And how this telescope works? First, we have the dome. This oh, it's a little white or gray that rotates in 360 degrees, and all of this hemisphere, and open in this part, and the light will go through this. Well, this is the sky. The light will come in through this part that opens, going to the primary mirror. The primary mirror is inside this part and has 3.600. I'm sorry, 3.6 meters above the. I don't know what's happening. 3.6 meters of diameter. Uh, So this is the telescope's body, and we have the primary mirror. The light reflects on the primary mirror, going to the secondary mirror, and this inside this black cylinder over here. And you can see a picture in the right part of your screen, taken in the top of the observatory. And this uh, black circle over here, these are a little of tabs that close the maintain clean and moisturize the primary mirror, and when the telescope is working, will be open to the primary mirror will be totally exposed to the sky, and the light then reflected by in the secondary mirror going through the a hole in the primary mirror that is gathered in here and send it to the instrument. Um, the instrument, this is a harps instrument. I think they already changed the instrument. I don't remember, but this is how harps works. The next instrument, and it is a exoplanet searcher by the spectra. So you can see a star in the middle and a planet rotating to the star, as we have our planet rotating to the sun. So we know that the star is a big object in the universe, has an interaction with with all of the planets called gravity, making them rotate into to the star like the sun. But the planets also have other interaction into their part, but it's a little. And this is the movement you can see like the shake of the star, and we can see through the spectra. The spectra is the rainbow of in the bottom part, and we have all of that black lines that move through the blue part and through the red part of the spectra. So it depends if the planet is going farther away from us or is coming closer to us. As you can see from here, so it's going further away, and the black lines are going through the red part. And this is the Doppler effect. We call it redshift and blue shift. This is how the instrument works. HARPS means High Accuracy Radial Planet Searcher. Um, this is the beautiful instrument that we have and very famous. So, a little about the how the telescopes moves. We have an equatorial mode. An equatorial mode was built in the old kind of telescope and controls the rotation, the movement of the planet. So this dark blue part will be pointing always to the south celestial pole because it's building in the south hemisphere. But with a telescope in the northern hemisphere, with this kind of mode and equatorial, will be pointing to the north celestial pole. So this is always pointing to that point. And we have the light blue part. This is like the telescope's body. When all of the all of the mirrors are put. So the movement will be like this. But we can see a video for a better understanding of how the telescope moves. Let's wait for the video, and we have it. So you can see that the light blue part inclinates in 90 degrees, with the dark blue part like rotating like this, as you can see in my camera. So that's how an equatorial mode can follow an object through the sky. Um, we have this telescope is of 3.6 meter of diameter, and the next telescope is near the same meter, but the newest telescopes building right now, for example, the BLT have 8 meters of diameter each one, and the future ELT will be near the 40 meters of diameter, but why do we need such a big mirror in astronomy? And it's because the light means everything in astronomy. With the light of an object, we can know its distance, the temperature, the, the movement that it has, the color, and which elements they have. So when we have the mirror is the one that collects all of the light. So when we have a bigger mirror, we will have more light collected, and we can get to fainter objects. And it means this means um, objects that are, for example, in the beginning of the universe. Uh, so some other numbers before going to the question part. As already told you, 3.6 meters of diameter with a thickness of the primary mirror from here to this point near 53 centimeters. And the mirror weighs 11 tons. That's nearly like two bigger elephants. And it was inaugurated in 1977. So I don't know if we have any questions for this telescope or for the observatory in general.
Well, I want to say that the new instrument it's called NIRPS, that it's for near infrared planet searcher. It does the same but with infrared light.
Yeah, because this one was in optical part of the wavelength.
We have a commentary here. It says, "Great to see this introduction to the telescope at La Silla Observatory complex. Wish I can visit it someday in the near future." Well, let's talk about the visits to La Silla Observatory. We have presidential visits every Saturday at night at 10 a.m. and 2 p.m. But not this Saturday, not today, because it's all snowy. This week there was snow. It's not good for astronomy, but it's really good for the environment because here the the cities are so dry and really need water. So it's good for one side because there's snow in the mountains, so we're gonna have water during the summer, but it's not so good for astronomy. And because of that, also not good for visitors because it's dangerous to go to the observatory. It's at 204,000 meters above sea level, and the road is not easy. So with snow, it's even more difficult. But at other times of the year, you can visit. You have to go to ESO.org page and search for visits to the observatories, and that you have to get to the facilities, and then a bus take you to the telescopes.
So now we don't have any questions. So let's go back again at the La Silla Plateau. We are going to the entity telescope. From this point, you can see the part of the mountain that has the shape of a horse saddle. And going to the entity telescope. And this telescope was inaugurated in 1989. Yes, nearly 10 years of difference with the other telescope. And the name is NTT, that means New Technology Telescope, because we have a lot of technologies applied in this telescope. One is the kind of the dome. So, as you remember in the other one, let me go to the other part. Uh, so, as you remember, you can see from here the 3.6 telescopes. We have a cylinder and a dome. This is the shape of the structure. But with this telescope, we have an octagonal structure from outside, and from the inside, you can see it's not as huge as the other. For example, you can see here a door, and a person will be like this height of average, and it's not as tiny as next to the telescope. Also, you can see that the telescope's body, this white part, is totally attached to the structure. And the new technology applied here was the mount. This is an equatorial mount. It's mean that we'll be moving. I mean, not equatorial, alto-azimuthal. It meaning that we'll be in moving through the altitude and azimuth. So the entire building is the one that rotates in 360 degrees. Uh, you can see, for example, we have some gates, and this circle curve, a curvature over here. This is the circle that will be rotating, and the building is in a platform of a kind of oil. And the white part, the telescope's body, will be inclining in 90 degrees. Another kind of new technology applying here, it calls active optics. But first, let me tell you about the primary mirror. In this case, the primary mirror has a diameter of 3.58, only 2 centimeters smaller than the other one. But the thickness of the primary mirror is only about 26 centimeters and weighs like 6 tons. It's like half the size of the thickness and the weight. And we have the gravity. Well, when the telescope works, we have the telescope inclinate, and the gravity works different in each part of the primary mirror. It's not seen by our eye, but can really change the quality of the image. So we have a little of actuators below the primary mirror in this part over here. We have uh, I, I think it was 77 actuators that going up and down to maintain the shape of the mirror to when it's inclinated, and this is operated by the operator. Um, and this is called active optics. Active optics was developed by ESO and made possible to build bigger telescopes with less material and focus more in the instrument the that in the structure, for example. Also, this kind of this kind of mount, the altazimuthal mount, is easier for the astronomer to use when we have better computers. So in the old time, we only use the equatorial mount because we didn't have all of the technology in computers, and it was best to track the object. Um, so it works. Let's go to the other part of the telescope, and it works like the same, but the dome is a little different. So as you can see, the entire telescope is totally exposed to the sky during the night. The light will be coming from the sky. Will go. I'm sorry, too fast. Um, go, will go to the primary mirror, reflect on that, go to the secondary mirror, and it's inside this black cylinder. Will reflect on the secondary mirror, but it's not going through the hole in the primary mirror as the other one. And in this case, we have a third mirror in this part, and it's inclinates in from 45 degrees to send all of the information to this room. Let me see where I'm going. In this room is the SOFI instrument that takes information, and this telescope takes image. No, it's not a spectrograph, but take pictures. And the instrument SOFI in this through this door works in the near infrared part of the or infrared part of the wavelength to to going through all of that gas and dust in the universe, and go, for example, looking through the Milky Way. And we have in this door, we can see, um, no, we can see the door, but it's the instrument that called EFOS that takes pictures in the optical part of the wavelength. Only one can be working at the time, during the night, and it depends in the kind of observation the astronomer needs, the the kind of research they are doing. And this optics is applied in the 10-meter category of telescopes and the ELT. So I don't know if we have any question like right now.
Yes, we have a question. It's a really good one. It says, when working on site at the observatory, is altitude sickness and lack of oxygen an issue to you?
It depends on in the health of the person. Okay, going for water. I don't know if Macarena can answer that.
Well, that it depends of the person, but 200, 2,400 meters above sea level, it's not that much. It has to be a person that didn't eat uh, before going to the observatory or something, because it's actually less oxygen. It's so dry, so you have to stay uh, drinking water.
Mhm.
It's not an issue. It's an issue, for example, in Alma, that it's 5,000 meters above sea level. There, people has to go with oxygen to work there.
But for
So,
example, I am, I don't know in English how we call it, but asthmatic. If you, so I can't run in the observatory, but I can walk and have a pretty nice day. And once we have troubles with some of the visitors, and I had to run, and I was need to use my um, inhalator. I don't know where I have, because I don't remember how it calls in English. Um, and we have some people that is not used at that height, 2,400 meters above the sea level, but in general, the people can work fine and see the observatories uh, without problems, without any issues.
okay, let's
Hmm.
go on to see where the astronomers work.
Yeah. So now, um, you can see a time lapse of a night of observation, and you can see like two big spaces. The one in the right part is all of the computers that work with the 3.6 telescope, and we have the operator that going back and uh, go to the computer and going outside the video, and he's the operator, the one that moves the telescopes, see the kind of the climate conditions or the instrument is if they are working fine, and the astronomer is the one sitting in the first computer, and in the left part we are the computers that work with the entity telescope. We have in this case two astronomers working together, and the operator that sit in the other chair, and I think it's working with the computers that have the information show of the actuators of the entity. Um, so the astronomers to go and observe in the observatories, they need to make a proposal. Uh, in the ESO, we have a committee in Europe that take all of the proposal of astronomers, the conditions they need to have, which kind of object they are observing, um, a little about the research they want. For example, if they need no moon, or it can be a moon, or for example a full moon, is really bothering us. But only the 20% of the proposals win a night of observation here at La Silla Observatory, and it's one of the most active observatories around the world. But the way the ESO rent the land of Chile is with the 10% of the night of a year, only works for Chilean astronomers, or astronomer working in a in a Chilean institute. And this committee is in Santiago that see the Chilean proposals. And the 10% of a night of observation is nearly like a month only for Chilean astronomers, and the other days are for international astronomers, because we have like from the three from the entire year we have nearly 300 clear nights to see the sky. Um, so in La Silla Observatory, the astronomer need to come here and do all of the observations. But example for in Paranal, they send the request, and astronomers of Paranal will observing and then send all of the data to the astronomers, and all of that data collected in the telescope is secret for the astronomer for 1 year. After that year, is openly published to all of the astronomers. Um, well, after this, the control room, we can see a bonus track, or the 10 milestone.
Yes, now we're gonna see the 10 most important discoveries of ESO. It's not with the last news, but pay attention, and then you can tell us which one is your favorite. We're gonna talk a little about that.
Las observaciones con los telescopios de ESO han llevado a muchos
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago. a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Well, as we could see, there's a lot of very interesting discoveries made with ESO telescopes and instruments. Pamela, which one is your favorite?
My favorite is the one about the Hubble constant, because I like the galaxies in the near years of the universe. I mean, the first years of the universe. And I really like how two kind of 2 different research teams get to the same discovery. So I really like that about astronomy.
Yes, the cooperation in astronomy is very important and
Mhm.
get you to really interesting and good and satisfying discoveries, to good answers. My favorite, for example, is the one of an exoplanet forming in an accretion disk. The image was taken with ALMA, and I really like that because it shows how we were formed. For example, here's some comments. It says, must be hard to boil water to make good tea at the altitude. It's not that hard, but it's different. And here, the favorite, Sagittarius A star, black hole stars. No way, the planet hunted. No way, the gamma ray burst. No, the exoplanet atmosphere. No, the universe expansions. Yes, they are so uh, good and interesting and favorite discoveries. They are so interesting. To see more information about that, you can follow the ESO.org page. There's releases of news. I'm gonna show you. We have here releases of news almost every week. This big image of a
Uh,
black hole.
Maga, Maga, you need to show the. Let
Oh,
me do it myself. I can do
yes.
it. I forget it.
Well, you can see the press releases. I'm gonna fix this. You have a lot of images, news. For example, this one, the Tarantulas cosmic web. Astronomers map violent star formation in nebula outside our galaxy. That's so far, so it's very interesting. Uh, you have blogs, images, top 10 images, and you can see also this virtual tour in the page. So take a look at it. And also in the social media, there's always a news and images, etc. Here we have the news of the new planet Hunter of
Mhm.
the Triple X telescope. And here's another one that the new solar panels of Paranal Observatory. So it's really interesting to see here. You can find more interesting discoveries that can be your favorite, maybe. Here we have greetings from Mexico. Así que saludos a México. And here another comment. The way that ESO constantly pushes the boundary of our knowledge blows my mind. And it's going to still like that because we are waiting for the ELT and all the new discoveries that it's gonna have. Uh, just like always, reading from Santiago. Saludos, Dahat.
Hello,
And
hello.
here, is astronomy more popular in Chile because of the observatories? Are people in general more interesting there?
I would say yes, but first, astronomy is beautiful as it is, so we don't doesn't need too many observatories to the people being interested in the beautiful image of the sky. But actually, here at La Serena or near La Serena, we have a lot of um, tourist observatories. So the people always go to that kind of observatory and they can see objects during the night, beautiful objects, but near our sun, for example, some planets, Jupiter, Saturn, some the moon, and some other constellations and nebula. But and also at La Silla Observatory, we have a lot of people coming, going to the observatories and visit us. Some schools, some groups of people. I would say that yes, because actually that the region that we are now at, the Coquimbo region, it's called the star region of Chile because we have a lot of observatories in Chile. I don't know what is your opinion, Macarena, but I would say yes.
Well, yes, there's popular here. Uh, for example, here in the region, in the northern part of Chile, where the observatories are, because of this kind of activities also. And
Mhm.
there's a lot of people in Chile that knows that here we have a lot of observatories, for example. And as Pamela said, there's no need to have the observatories for people to like astronomy and get interested in astronomy. For example, you are here. I don't know if you have too many telescopes of observatories where you're from. Okay, let's go to the last part of the tour. It's one of the most beautiful. Pamela can show you.
Yeah,
Well,
I'm going
another
there.
another question before we go. When scientists climb number of 30 billion stars, it's almost laughable how much blind faith that requires. I didn't
Mm,
understand the question actually.
I think that is that part of the much blind faith that requires is like the exact number we are telling, but I don't know if this is what you mean, but in astronomy is all about probability and statistical. So, um, for example, we have in some part 30 billion of a star is um, um, there are some calculations of how should be what number of stars should be with this kind of brightness of this object. But there are a lot of calculations, and we have some a paper from a year telling something about this object, and then we have another group with another paper 2 years later refuting that number or comparing that number to the results. So the science move like this. We have something, but a group doesn't think they were correct, so they try to try to corroborate if the number is correct. So they make another observation. That comment is not fate; it's science.
Yes, that's
And
exactly. Also, for example, the that huge numbers are statistical. It's not an exact number because we can see a part of the universe and take measurements of the number of stars there, and then another one makes the same observations with other techniques or with the same looking for uh, other parameters, and then with a lot of research we can get to a conclusion that it's an approximate conclusion, it's not the exact number. And in science everything is always open to be changed uh, with new observations, with new discoveries, and with new science. So
yeah.
first we thought that we were the only planet around a star, and now we know that there's more than 5,000 exoplanets beyond the solar system.
And that's
So it,
also why we need different kind of telescopes. For example, one that observes in the optical part of the wavelength, in the infrared, in X-ray, in gamma ray. Because the, for example, in the Milky Way looks different in each part of the wavelength, and the distance of an object in the X-ray could be so different with the distance in the infrared or the distance that we can calculate in the gamma rays. So we need to get together all of that information, gather all of that information, and to estimate which is the best one. So that's why we have a lot of collaboration in astronomy. Some papers that have more than 300 people working on that paper.
I'm gonna show you something about what Pamela said uh, about these uh, different ways to see the Milky Way. This is how we see usually the Milky Way in optical wavelength, that it's the one we see with our eyes. But if we see the Milky Way, for example, with ALMA, we're gonna see something like this. And we have a lot more of information, more than we usually know with visible light. And also with different wavelengths we have different information, we see different things, we can measure uh, different things. So uh, yeah, there's a lot of study to have a result that when you have more technology to see more, it's gonna be maybe different. It's not gonna be the same result.
Yeah, so ah, there were too many questions, and we
Saludos desde Colombia, así que saludos a Colombia.
salute. We
And
have
now we
too little time left, so let's move to the other part. We have just 8 minutes.
yes, so
Um,
let's see the final part of the tour.
so we are going out from the entity telescope. I don't know. You can see my okay. So now we are going out from the entity telescope, and it's getting late. Uh, First, you can see the octagonal structure of the entity. Uh, this is the dome, and it's really amazing how the sky is from this point. Uh, Actually, we don't get to use. Uh, we don't have the opportunity to be at the night as a guide. I mean, I and Macarena, but it's really amazing. We once have the opportunity to stay during the night. It's really, really amazing. So first, start with Orion's constellation. This is like the most famous constellation here at the southern hemisphere. And from all of the people watching us from the northern hemisphere, you can see something different in Orion. Uh, and it's because it's upside down. So we have Betelgeuse over here, this red giant star. We have Bellatrix. We have Real and Saif. And in this right part, we have the Orion's Nebula, and also in this part is another part of the Orion's Nebula with the Orion's Belt, as we commonly know as Tres Marias. Moving, going up, we have Sirius star next to the Orions, and this is the main star of the Canis Majoris constellation. And we have here the feet part of the dog, the tail, the body. We have the over here. We have the main the the front the front feet, the head. I get lost in the head of the Canis Majoris because there are too many stars, um, and, and it's a picture. But what else I can show you that is more it's beautiful, and these are the our neighbors. We have the small Magellanic Clouds and the large Magellanic Cloud, and those are stars that are rotating our the Milky Way. Our I mean they are not the stars; they are galaxies that are rotating our own galaxy. For example, the the news that Macarena read about the Tarantula Nebula. I don't remember. The Tarantula Nebula is over here, and the Large Magellanic Cloud, and this has um, a shape like an irregular. These are irregular galaxies, but this one has a shape of an arm, like irregular spiral galaxy, and this is so faint and diffuse. The small Magellanic Cloud, and these were the name are because of the circumnavigation of Hernando de Magallanes um, a long time ago. And clearly at that time, they didn't know what a galaxy was. So now we know that a galaxy, they are a lot of stars together. Then we have the Milky Way. In the Milky Way, with the Milky Way, we can know one interest point in the universe that uh, it's not the universe, I mean in the sky, that we call it the South Celestial Pole. And it's very important in astronomy because of the Equatorial Mode, for example, and all of the objects in the sky will be rotating to that point. So if you can see you have seen one image, one exposed image of one night, you can see that all of the stars will like moving in circles, and one point is static, and this is the south celestial pole. So how can we find it? There are two ways. The first one with a small and large Magellanic Cloud, and we can make a triangle with the all of their part equals. So 1, 2, 3, and near this point we can have the South Celestial Pole. Another one is the Southern Cross, that another constellation, and we have these stars: 1, 2, 3, and 4. So if we have the 1 and 3 stars, the major axis of the croix, and count to 3.5 part, we can have the South Celestial Pole. So let's go together. 1, 2, 3. Um, let my mouse. No, and again. 1, 2, 3.5, and this is the point of the South Celestial Pole. But something that I really um, have interest is in know about the constellation that the people living in the old times near my place, at the Andes Mountain, they also have constellations, but not like the Greek one, like point lines together with the points and some um, like Orion, some with imagination. But actually, the people in the Andes, they saw the different colors in the Milky Way, and so animals. For example, in this part we have Alpha Centauri. Alpha Centauri is the nearest star of our sun. Actually, there are three stars: Alpha, Beta, and Proxima Centauri. Proxima is the nearest to us. Like, uh, but we have in this something like a head, and this is the head of the llama. The llama is the typical animal that you can see at the Andes Mountains from uh, Peru, for example, Machu Picchu to uh, Valparaiso. Mm, I don't get, but they have a lot of range in the Andes. So we have the head of the llama, the neck, the body, and the back feet, the tail, and the front feet. And next to the llama, we have a tiny llama over here, just in the top of the 3.6 telescope. And we have over here the head of the llama, the ear, the neck, the body, and the the feet. So it's like jumping that llama. Also, they have a fox, a frog. I think the frog was over here, but I can't really see it. And we also have a snake. The snake is easily found, and you can see this black part over the Milky Way, and with a sinusoidal form. And this is the snake. So I really found that amazing. And also, I have some other objects very tiny. And let's go back to the 3.6 from the night because it's already late. And we can see the 3.6 telescope, the halo of the light pollution of La Serena, and that's how we get to the La Silla Observatory. Um, we have also the Milky Way, the beautiful sky, the light pollution coming us from the rock, the nearest city, Copiapó, Vallenar, and over here you can see the light pollution of Argentina. So it's it's really bothering us, the light pollution at to the astronomy, and not also in astronomy, also the animals, the The health of the people also is bothered for the the light pollution, and it's going late. You can see also from here the large and small Magellanic Clouds, some um, small telescopes, and this is the end of the tour. We are at the coffee break, and this is the photographer that made possible this beautiful tour. In this hotel, all of the astronomers that make all of the observations can sleep, eat, and make recreation. We have libraries, cinema, gymnastic, but only for the astronomer and the operators. Um, so I don't know, Macarena, if you have anything to say.
We have a very interesting comment here. I really love it. It says, back in the days, remember I saw the nebula Orion at the Cerro San Cristobal. Literally, fui a la punta del cerro. Yes, we also go to La Punta del Cerro when we go to work. And
Yeah.
yeah, it's funny. It's really beautiful to see the astronomical objects.
Yeah.
Well, I think that's all. Thank you so much. Here, Pamela Macarena and team, thank you so much. I'm looking forward to the next tour and to new discoveries for ESO. Yeah, every Saturday we have these virtual tours. 1 week to La Silla and the other week to Paranal. So stay checking for the tours. Another comment here: astronomy is always looking up. Thank you so much, guys. Really enjoyed the tour. Thank you, Com. Thank you for joining us, for your comments, your questions, for your attention, and we really hope that you have learned something, you have leave something in your mind, and that's all for me.
Um, it's the same. I hope you have enjoyed the tour. Thank us for watching us. Thank you for watching us. I really hope you can visit the observatory at the present. I hope seeing you the next time.
So, see you. Goodbye.
Goodbye, everyone.